midterm. We'll have some things in common with that midterm and some things that are different. I will emphasize this. I'm not going to be asking you to write any C or C++ code on the midterm. So you may be asked to describe algorithms, but you'll be asked to do it in pseudocode or English rather than actually, it's a midterm. There's 65 minutes. No, I'm not going to ask you to run Valgrind on a piece of paper or do anything. If you want to, I won't stop you, but no. It ain't going to happen. It ain't going to happen. Thanks for the memory. You know how that works. You get to bring in the cheat sheet, put your name on it. I'll collect them at the end. You have to show your ID at the end of the quarter, although at this point I know all of you anyway, and if you bring in a ringer, I'll figure it out. So that all works. And you know about the material in the textbook. A lot of what we go over in the lectures also appears in the textbook, except for my snide remarks and bad jokes and codas, which do not appear inside the textbook. Before I get started, any questions about the midterm that people would like to ask? Okay, again, you can post things on Piazza that end up dealing with that. And of course, I'll emphasize, we'd like you to try to continue to use your teams, but if there are issues with respect to teams, let me know and we'll see about adjusting how that goes. And there are always people who discover that this course, when I said it was a difficult systems course in 180 and very different from 180, that again, I was telling you the truth. It is a very different sort of course. I'll make this remark several times about Project 3. Project 3 is about building indexes, and you will have to build B-tree. And the work that you did on the RBFM will end up helping you a lot to be able to do it. And there are two types of nodes that you have in a B-tree. There are leaf nodes and there are non-leaf nodes. And you are going to have to represent both kinds of nodes to be able to do this project. Okay? Now, here's what almost everybody decides that they want to do in this course, and I'll warn you off it from the beginning. They start saying, oh, I've already built the RBFM layer. And I'm trying to represent index nodes, either the leaf or the non-leaf index nodes. And so I'll just use the RBFM and treat those as being records and see if I can fit it into the RBFM layer. It doesn't work. The ideas that you use to be able to build the RBFM layer can work, but neither the non-leaf pages that have these traffic cops and keys and so on in them, that search keys that help you go where you want to go and pointers to pages, neither the non-leaf pages nor the leaf pages really fit into what the RBFM layer does. So what you learn to do when you build the RBF layer will be very valuable to you, but don't try to use it to what you did with the RBFM layer. A fast joke just to lighten, old joke about a mathematician. Mathematician goes to sleep in a room and there's a red bucket and a bunch of water and a fire breaks out. So what does the mathematician do? Puts out the fire using, putting water into the red bucket and puts out the fire. Second story, the mathematician is sleeping in a room. He's got a blue bucket and he's got a bunch of water. Fire breaks out. What does the mathematician do? Paints the bucket red, reduces it to the solution to the previously solved problem, and goes back to sleep. You can't necessarily reduce things back to other problems and regard them as solved. It's not necessarily a good solution. All right, end of joke. Where are we? Again, this lecture is not on the midterm, it is on the final, so it's not a bad idea to pay some level of attention. There are a bunch of different operations in relational database that we'll have to talk about. I told you in 180 that relational algebra has a fair amount to do with thinking about how execution plans work, not exactly the same, but similar. And these are 6 operators that we're going to talk about. We've already talked about join. So you've seen a heck of a lot of different join ways of implementing join, and there are many, many more. But you've seen a lot of the major ones to begin with, and this lecture is going to be talking about the remaining 5. And the idea is that what's important is that you have not only composition and SQL in writing your queries, but also the relational algebra operators can be composed together. And so if you have an execution plan that computes part of a query, then the next operator, either by using pipelining or taking a stored result and using it, it can be used as the basis of what you do for the next operator and what's going on. And then what we're going to do is we'll talk about query optimization. There'll be 2 lectures, query optimization part 1 and query optimization part 2, where we mostly talk about how this worked in System R, but a lot of the System R principles are still applied in existing relational operators, but extended in important ways. Boring slide. I told you to get sick of sailors and reserves, but since we're going to be talking about them again, just repeating that slide so we can talk about what's going on there. You know all about this stuff, and you know about all this stuff, and the notation that I use in talking about pages mostly. Okay, so let's talk about selections. And we already did this. I'll just remind you about how the thing works. You've got a query that involves a selection. And we're going to go with our boring 20-letter alphabet just as a way of being able to make the math simpler. So we'll assume that all the reservation names start off with A through, not Z, which would be 26 letters, but A through T, which would be 20 letters. There are 20 letters in the alphabet. And so basically the cost of doing things when there's a selection is going to depend on what number of tuples end up qualifying. It also depends on whether or not, if you're using an index, whether or not you end up having clustering in the index. So, if you do end up having an index on reservation name, then the cost of using that index to be able to get the reservations that are less than C. Well, again, we're making this stupid, naive assumption. The naive assumption, and we'll talk about relaxing it later in the course, is that if there are 20 letters in our slightly demented alphabet, everything which is less than C has to begin with either A or B. If we assume uniform distribution, which you can't assume anything else, and you have to guess anyway, it's as good a stupid assumption as any, right? Because you've got 2 out of 20 letters, so we'll assume that 1/10 of the tuples are going to end up qualifying. So since you get 10% of the tuples qualifying in our 20-letter alphabet, that's going to end up being 10,000 tuples, and that will end up being 100 pages. And if there's 100 index, that's all you have to touch, 100 pages. When I say that the total is 100 pages, that's what the total of the answer would be. But if it's clustered, you only have to touch those 100 pages. You start the far left leaf of the B tree, and you keep going until you hit a C, and then you're done, and you only touched 100 pages, which is going to be 1/10 of the pages, 1/10 of the tuples, and that's great. On the other hand, if it's unclustered, bing, 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 you keep hitting all over the place. So you follow the unclustered index, it tells you, all the things in order from A up to C. So searching in the index is nice, but then the data, you might hit things all over the place, which might cost you 10,000 IOs. Here's an important improvement on the slide, which I've already told you, that in this particular case, you look up all the RIDs using the unclustered index. You sort the RIDs based on, because an RID is just a page ID and a slot ID, you sort the RIDs based on the pages. And then you get them in order. What the heck, I could even sort them on both the page IDs and the slot IDs, so I'd even get the slot IDs in order if I wanted to. Not that that particularly matters. But basically what that does is it ensures that the pages are only touched once, the data pages. So that ends up being something which saves you a lot of work. What I do want to emphasize, I've mentioned this before, if I access based on the index, I'll get my results in R-name order. But if I do the sort, I'm only touching each page once, but I don't get my results in R-name order. Win some, you lose some. Does it matter whether or not the results are in R-name order? Well, I don't have an order by. If I had an order by, it would matter. So, win some, lose some. Question on this? We've gone over it before. So there are several different approaches. This is just a couple of them. I'll mention 1 or 2 others that you can use to trying to do selections. You can find the most selective access path, find tuples using it, and then apply any other predicates that are there that the index doesn't help you with. The index can help you with some of the predicates, but it may not help you with all of them. So what does it mean to be the most selective access path? One of the ways of figuring that out is the one that will require the least amount of IOs, and get those. And as you get the tuples, you can apply the other predicates, the other terms that are there, and reduce the number of result. An example that we looked at is if you have day less than August 9th, 1994, BID 5, SID 5. We looked at this exact example already. If you have a B tree on day, then you could go ahead and just extract the things that have the right day using the B tree, and then check on the BID and SID predicates. Or if you had a hash index, because you have the two equalities on BID and SID, if you have a hash index on BID SID, then you could just get the exact right things that have BID 5 and SID equals 3 inside reserves. Then you still have to apply the predicate on day. You might pick the one of them that's the most selective in the sense of fewest number of IOs. You might also pick the one of them that's most selective in terms of returning the fewest number of tuples. Or, if you happen to have both indexes, you might do RID intersection. You might only take the RIDs that do both. Of course, that requires that you do the intersection via sorting or hashing or whatever. But that can end up being a win because avoiding having to touch irrelevant data ends up being really significant in reducing the cost of what you're doing. And in fact, that's, if you have two or more matching indexes, that's what this thing says. You can apply multiple indexes, not just one. Now, which is better? It depends. Costing these things out ends up being tricky, and then actually figuring out whether or not your estimates are right ends up being important. I'll give you a theme that I will be mentioning as we talk about optimization, which isn't emphasized in the book, but it's really worthwhile. When you're trying to pick a good plan, it's often most valuable to pick a plan where you know what the heck the cost of the plan is and you have low variance on the plan. So for example, suppose that you have a plan where it sometimes, let's say 80% of the time it costs 500 and the other 20% of the time it costs 20,000. And you have another plan which 98% of the time costs 1,200. You might be better off picking the plan that is pretty darn good 98% of the time, as opposed to the one which has 20% of the time is going to be far off. Predictability ends up being good. Predictability with a good result ends up being good, as opposed to swinging sometimes good and sometimes bad. So you may want to go ahead and pick a plan where it ends up being predictable, or maybe you can figure out the cases where the thing that's 20% off is bad, and if you can tell you're in the 20% case, pick a different plan. I've already told you, if I'm trying to look up people based on a state, and there's a parameter given, give me all the Santa Cruz students who come from Georgia. There aren't going to be that many people from Georgia, it's going to be fast. But if my parameter, which might be a variable from my query, if the state that I'm looking for is California, maybe that's the case where it takes a lot longer to be able to do. But I might pick a different plan based on my input parameter. I'm looking to show all the students from California. Optimization is a hell of an interesting, difficult subject. So I'm just trying to show you some of the variations of it that show up here. Okay. So again, you can go ahead and use a variation of index intersection to be able to play with it. Okay, now we're going to get to projection. As I've mentioned before, it's always kind of amusing that the select clause does projection and the where clause does selection. But I didn't mean these things. I can't do anything about them. Okay, but the select clause is what does projection. And the hard part of projection, if all I'm doing is saying, I've got the 12 attributes and I only want 5 of them. Okay, pretty easy. Maybe I can get rid of only keep the 5 attributes early so I don't carry around irrelevant 7 attributes as I do them. The hard part of projection is that remember that the syntax of SQL, when you have select distinct, is you get rid of duplicates. So the hard part of doing projection isn't getting rid of the irrelevant attributes, it's eliminating the duplicates. So here's one of the things that you can do. Okay, you can do an approach based on sorting. And so basically what you can do is you can sort to get rid of duplicates. And if you have the external sort, it doesn't all fit inside memory. You can take the algorithm that we already discussed in lecture, whatever it was, 7, 6, I forget. When we talked about doing sorting, remember that pass 0 in that approach basically says first take each page and, you know, go ahead and sort the page, and then we're going to be using this external merge sort to be able to put them together in, you know, this number of passes that we talked about, right, where it was, the cost was 2n times 1 plus log to the base b minus 1 of n divided by b. Okay, so that was the formula that we used. Well, in pass 0, you're taking everything that fits inside a page and you're sorting it. So you're bringing in all the data. Why muck around with the things that you don't care about if you're going to be doing a projection? If you're going to be doing a sort based on a bunch of fields and trying to bring in as much as you can into your blocks, you've got 12 fields, you only care about 5. If you've got 1,000 fields and you only care about 3, you can jam a lot more on the page and also reduce stuff for the, you know, subsequent phases by only keeping 3 fields that you want to keep that are part of the sort and things that you need later. But by the way, you do have to keep the sort fields as well as things that you want in the answer. Usually the sort fields are things that you want inside the answer. The order by fields are things you want in the answer. Not necessarily, but you got to keep those around too. So basically, as you read in the blocks to prepare to be able to do the sort to get rid of duplicates, don't bother keeping around stuff that doesn't matter. It's not, maybe it helped you earlier, but you know, what have you done for me lately? If you're not going to care about it later, for example, if what you're trying to do is do the sort to give you the answer, and what are you sorting by when you're getting rid of duplicates? Everything. So if you have a select distinct where you're asking for 3 fields, you need the 3 fields. And things are duplicates if they agree on those 3 fields, right? If you're doing a select distinct and there are 8 fields, you care about the 8 fields and it's a duplicate if it agrees on all of those 8 fields. 7 out of 8 ain't good enough. 7 out of 8 means it's not a duplicate. So you're trying to do a select distinct, getting 8 fields out. Don't bother with the other 992. Just keep the 8 fields that you care about. You sort based on those. You fit those 8, you fit a lot more inside your blocks if you only have to deal with 8. So you do the projection, rather than do the projection after you do the sort, you do the projection before you do the sort. You push down projections, right? So that can end up really reducing the amount of space for what you're dealing with. Instead of having a record that has, you know, 1,000 bytes in it, you're dealing with a record that has 30 bytes in it, which means you can fit more records inside to be able to do it. So that ends up being really nice because you've reduced things down. Now the other thing is that when we did a sort, we kept duplicates. Duplicates can matter. You may be doing an aggregate later or something else. Getting rid of duplicates, sort doesn't get rid of duplicates unless you want it to. You can write a sort that gets rid of duplicates. And that's what you want to do here. If you're doing the sort, it's not something where, let's sort everything and let's keep the 500 duplicates we have of this row, and then we'll get rid of it later. As soon as you discover when you're doing your merge that you have things that are duplicates, yeah, you care about it. You keep one of them. You don't keep 500. You don't even keep 2. A very simple optimization. When you're doing your sort, and you figure out where something goes, anytime there's a tie, you don't bother keeping all of them, you just keep 1. That's all you need. So basically what you're doing is you're keeping track of which attributes you care about, which fields you care about, and only keeping them. And you also don't have to keep around duplicates as you find them. As soon as you find a duplicate, you only keep 1. As soon as you merge and you see that these things are duplicates, you only keep 1. So you're merging, you know, k things together, and each of them has the same tuple. You only keep 1. Okay, so that's the way the thing works. You only have to deal with the columns that you care about, which are the things you have to select distinct, these 8 columns, you only keep those 8 columns. Columns, attributes, fields, I'm using synonymously in this class. And when you merge, anytime you find a duplicate, there can be only one. You only keep one, there's no point. And so if you end up having something where the size of the projected thing, where you only keep what you care about for the select, you reduce by 1/4 from 1,000 input pages to 250 input pages when you're doing the sort. So phase 0 could end up, reducing incredibly. And then later phases reduce not the number of columns, but the number of rows, because as soon as you find duplicates, you get rid of them immediately. Of course, you have to continue that all the way through the end, so you don't have duplicates at the end. Now, the next thing that I expect somebody to ask me, because I've already told you this, is sorting is a wonderful n-log-n algorithm. Why do I want to bother sorting if what I'm trying to do is to eliminate duplicates and I don't have an order block? So this is where the magical hashing stuff comes in, where we can use the same kind of ideas that we've talked about before to use hashing to help us deal with select distinct. So instead of going ahead and bothering with the sort, what we can do is we can read the relation R where we're only selecting a subset of R, and we go ahead and we read tuples, and as we reading a tuple, again, we discard the irrelevant fields. We keep the ones that matter, and we use the hash function. We use a function h, or we'll call it h1 over here. We'll use the function h1, and we'll put tuples from R inside a hash table. And then, we pick an output buffer in which the thing ends up going. And assuming that we have, let's say, we have a total of B buffers, so one of them is for a block of R, and the other one is for outputs. And so we're producing B-1 hash buckets. This should remind you of stuff we've already gone over with things like the block sort and the hash, the Grace hash, the hash join and Grace hash join, and also the block join block-oriented join that we looked at. So what we do is we put things into these buffers, but of course, again, there can be puns. Things can be put inside the same buffer even though they have different values. Now also, if the same exact value is put into a buffer more than once, we can get rid of it immediately. Again, we're looking for select distinct of the following 8 fields. A, we get rid of the other 992 fields, because all we care about is the 8 fields that we're having as select distinct, these 8 fields. And also, when multiple things get put in the hash table, if we could bother checking to see if there are ties, and get rid of ties there. But maybe, let's just make it easy. Let's say we're not getting rid of ties as we go, and we're just throwing it into the hash bucket. This would be too much work to get rid of ties now. Now we have buckets. Each of the buckets has a bunch of things in it. And we want to get rid of duplicates from each bucket. I'll make the same observation that we made last time in a different context. The problem that we're dealing with, because if they're duplicates, they have to be in the same bucket now. The problem that we're having to deal with, getting rid of duplicates from each bucket, is exactly the same problem that we started with. And also, I will point out that although there are a whole bunch of tuples inside the same bucket, that may be a lot of different pages. We write the things that go, whose hash value is 17, into R sub 17. A hash bucket, the block for R17 fills up. We write that bucket out to persistent storage or something else. And then we create the next block for hash value 17, and so on and so on. So there could be a whole bunch of different things. R17 might consist of 100 different blocks that are out there. But the problem we have on eliminating duplicates from R17 is exactly the same problem we started with R. Do you know what we can do? Of course you do. We can recurse. Curse again and again and again. Right? Dirty words, we're recursing. For each one of the partitions, for R17 and all the other ones, we do the same kind of thing, but do we use H1 again? No, that would be insanity, because everything that's in R17 has hash value 17. So we pick a different universal hash function, H2, which is different, which again is only working on the fields that we care about. We don't have to bother dealing with the other fields. We've gotten rid of them, they're irrelevant. And we do the same kind of thing again. And we can do this recursively whatever number of times, picking different hash functions each time as a way of being able to do this. And so, you know, however many times this can be done independently for each one of the partitions. And we can pick H1 and then H2 and then H3. We could use H2, the second part, for all the different R's, as long as H2 is different from H1. Or we could use different ones, but we might as well just use the same H2 to be able to do it. And one of the wonderful things about the algorithms we're looking at with hashing is that these can be hugely parallelized. If I used a hash function and I created, you know, 1 through 1001 partitions, I can get rid of the duplicates from the 1001 partitions in parallel. There's no reason why I have to do them on the same CPU with the same memory. I can have lots of cores, lots of memories, etc., and do this hugely in parallel. So got the idea? And the hashing is going to be typically a lot faster than n-log-n. Remember the bad case that I told you about, though. If everything skews and has the same value, I mean, it doesn't matter how many times you pitch hash functions, they're all going to be placed inside the same area. You still have to deal with that case too. So the sort pace approach used to be the standard, and it doesn't get affected by that skew with the same value appearing a lot of different times. The result is going to end up being sorted. Oh, the nice thing is that you can end up eliminating. This is better than doing with the join. With the join, you have to keep duplicates around. With this approach on projection, if you have a duplicate, exactly the same fields, you really can get rid of it. So actually, the duplicate, if it's exactly the same value, it really does work nicely, because you can get rid of duplicates and equal. You don't have to keep the duplicates around. An approach based on Grace hash join, the Grace hash approach is very common. Again, that's the same kind of thing that we're talking about before. You could use other approaches which are, you know, discussed in the book, which have, you know, different ways of playing around with tricks with memory. But the main thing is the Grace hash approach. Again, this thing with the H1, H2, H3 kind of thing, building tables. That's the approach that's used. Suppose that you have an index that has, you know, you're sorting based on 3 attributes. Suppose that you have an index that has, it's an index on 5 attributes. Indexes can be on lots of attributes. So you have an index that's on 5 attributes. The index is on A, B, C, D, E. And you have a situation in which, you know, what you're looking for is, let's say, you know, B, C, E. Then you can get the results. Suppose that you want to have select distinct BCE, you know, from your result. Then again, you don't have to touch the data. If you're looking for select BCE and you've got an index on A, B, C, D, E, you can get it from the index. You're still going to have to sort the index tuples to get the distinct BCE values, right? But you have to sort the index values on BCE to get rid of duplicates. Ignoring the A and the D, you just get BCE, which is a lot cheaper than having to touch all the data and, you know, play with all the data. So that looks really nice. If you have a B tree index, and by the way, you can do this with a hash index as well as with a B tree index. If the hash index, you're hashing on A, B, C, D, E, then you can scan the entire hash index and sort based on the BCEs and not have to touch the data. Question on this? Again, you can always scan the entire hash index, which means going through all the buckets and get everything out of it. Because again, then you don't have to touch the data, because A, B, C, D, E is inside the index. You just go through everything inside your hash index. If you have a tree index, and if it happens that the attributes that you care about are the ones at the beginning, so you have a hash, you have a tree index on A, B, C, D, E, but let's assume that you're looking for ABC, the distinct values of ABC. you don't have to sort the index, you can just walk through, and every time you have a new value of ABC, that goes in your answer. If you want the distinct ABC, if ABC is a prefix, that makes life easier. You can put things in the answer. If you're looking for ABD, you could use the index also, but it'd be a little bit harder to do because there would be all these C's in the middle, but you could do it. So there are lots of variations of techniques that you can do. And again, you can get rid of duplicates. If you're trying to get things based on ABC, you just march forward. Every time you have a new value ABC, you put things in. If you're looking for ABD, it would be a little bit more complicated. But again, you can get it using the index. All these different tricks are used by optimizers, and many, many, many more. Okay, so basically, you can always go ahead and pick. We're not talking about simple. Simple, tries to assume that everything fits inside memory. Hybrid is something that does something clever with partition 1, but it's not worth going into. You can always go ahead and do what we've talked about. What you do is you partition in the first pass in Grace hash join, and then in phase 2 you may have to recurse, and then you may have to recurse again, which is phase 3. And you play, remember that square root of the pages of R thing, M is the pages of R, sorry, I didn't replace that one here. You can play that, square root game to be able to, go ahead and fit things in. So if the amount of memory you need for R17, because now I'm trying to get rid of duplicates from R17. If the amount of memory I need for R17 is less than or equal to B squared, in other words, it's that square root of M thing, then, I can make things work nicely as long as there's no skew and fit things inside memory. So general idea of how that works. It's a variation of what we talked about for the hash. Okay, now what about other operators? Well, as you may remember, intersection and cross products are going to be special cases of join. Intersection is a join on all attributes. If I have R of ABC and S of ABC, and I want to take their intersection, it's basically saying RA equals SA, RB equals SB, RC equals SC. It's a join on all the attributes. Cross product, which you try to avoid, Cartesian product, is also a join, just with no predicates. Right. So we've talked about join algorithms. We can take advantage of them before, although again, cross product is something which is pretty dumb, combine everything with everything. Union in SQL, union should be called union distinct, and you can write union distinct. But if you just say ordinary union, it corresponds to union distinct. Well, actually, let's start off with union all. How can you do a union all? You have R, you have S, jam them together. You don't have to put them in any particular order unless there's an order by, just concatenating everything together is what union all does. You don't care about the order, you just, pipeline everything in, from R and S or whatever it is to do a union. Union distinct, we're going to say the same thing that we did before about getting rid of duplicates. Union distinct is just like union, except you want to get rid of duplicates. So you can go ahead and you can sort R and you can sort S and traffic cop where you only keep the things that appear once. Don't keep them more than once. So if you have duplicates in R, duplicates in S, or something that appears in both R and S, you get rid of it. You only keep one when you have union distinct. So that's the way that it works. And again, you can do the trick. If you're sorting R and you can sorting S, you can also go ahead and do things a little bit faster by getting rid of duplicates as part of the original pass zero kind of approach to be able to get rid of duplicates as you go. Because basically, if you're trying to do the union, you basically can say, I don't have to sort R and sort S, I'll just sort both R and S. In other words, basically just take R and take S as if they were one relation, because that's what they'll be when you do the union. and just use it as if there was one big thing that I was trying to go ahead and do duplicates from, same way that we did, the operation before for getting rid of duplicates. You could also go ahead and use the Grace hash approach to be able to get rid of duplicates. So you can do the same kind of thing, partition both R and S as we did with the Grace join using the hash function, and you end up building a table. And what you're going to do is you build a table where you end up having the let's see, you've built R17 and S17, and same thing for all these different values, each RI and SJ, and you got rid of duplicates from the R's as you built them, or maybe you're getting rid of duplicates as you go. What you're going to do is, for each S partition, so for example for S17, what you're going to do is you'll build a separate hash table using a second function, and then you'll do the same thing where you go through the R partition, and you only put things inside the answer when they end up not matching on both H1 and H2. And again, you can recurse down to H3 rather as you go as well. It's really just taking R and S together and getting rid of duplicates to be able to make it work. So there are a lot of different variations that you can use. Yep.
So in that case, would you need to get each, I guess in each bucket, get it down to just one entry? So that way you can be sure, because different values can hash into the same entry, right?
That's absolutely true, but you don't have to get it down to one. You can just get it down to so it fits inside memory, and you can distinguish between them.
Oh, okay.
Right, so that'll work. So for the table that you're building inside memory, you only have to keep each tuple once. So as long as it all fits inside memory, then it ends up being fun. Okay, now we're going to talk about something with aggregates. We're going to talk about an easy case first. That's a case where you don't have any group by, and then we're going to talk about a not much harder case where you do have group by. How many of you have heard of MapReduce? How many of you know how MapReduce works? What you're about to see is something which is an ancestor, a very close ancestor of MapReduce. In fact, one of the slightly sillier exchanges that occurred inside this field occurred between the people who did MapReduce, Dean and Gammelwatt for Oracle, and people who did very, very similar things, Mike Stonebreaker and Dave DeWitt, and all incredibly great people, where they tried to debate about, did you use our work without referencing it? Because there is such a close resemblance of what's going on with what was done in the distributed database for dealing with aggregates and group by. MapReduce is just a variation, except that it's an important variation in a much larger scale environment that builds on similar ideas that was probably discovered independently. But you should understand, regardless of the politics, and they eventually ended up converging. Just understand the technical ideas. So suppose that you're trying to do one of SQL's aggregates, and if you don't have grouping, then you potentially have to scan the entire relations to be able to do your aggregate, to be able to find what the values are. On the other hand, if you end up having an index that includes all the attributes that you need for what's going on, then you can take advantage of the index without having to touch the data. So you need everything that you need for the select where and for the aggregate. So it's not just the including the things in the select in the where clause. It also needs the stuff